Good afternoon. Welcome to lecture 13.2 of group theory course. This is the second and final lecture of chapter 13. And we are going to start from where we stopped last time. We were discussing the K.P perturbation theory in the context of analyzing the degenerate states, for instance, at a certain symmetry point in the Brillouin zone, and how this degeneracy is broken when we move away from this high symmetry point along any given arbitrary direction in the first Brillouin zone. So in general, this is the idea. We have a set of degenerate, or how they call them, nearly degenerate states with the label N or M, and there's a coupling in second order perturbation theory to other states at the same point in the Brillouin zone, for instance the gamma point, and this coupling is responsible within the K.P framework, is responsible for the how degeneracies are broken when we move away from the gamma point, and precisely one can use that also to calculate effective masses, for instance. And the specific example we were discussing was, for instance, threefold degenerate levels at the gamma point that transform according either to the gamma 1,5 minus or the gamma 2,5 minus representations. And these are the secular equation that one needs to solve. One needs to diagonalize this matrix, and each one of these matrix elements in second order perturbation theory is going to be given by this expression, in which again alpha are what we call the intermediate states at the gamma point. All right. So and also we mentioned that using group theory one could conclude that in many cases, most matrix elements of this type are related by symmetry. And for instance, if you consider matrix element between gamma 1,5 minus alpha being x, y, or z, and the an intermediate state with the symmetry gamma 1 plus, for instance. So it's basically the same quantity multiplied by k alpha, the alpha component of the wave vector, right? And you have many different relations like that for the gamma 1,5 representation, and also for the gamma 2,5 representation. When the gamma 2,5 representations, one just need to be careful. What we use the following notation: gamma 2,5 x, y, and z are related to basis functions y, z, x, z, and xy. All right. So this is all tabulated, and we are going to use this information in order to calculate this matrix for some specific cases. So let's assume that now we are focusing on a gamma 1,5 minus level, and the perturbation Hamiltonian transforms like a vector in K.P theory. So we have discussed this last time. So the direct product between these two representations, when we decompose it, gives me this set of levels, this set of symmetries: gamma 1 plus, gamma 1,2 plus, gamma 1,5 plus, and gamma 2,5 plus. So when we analyze these matrix elements, then these are the only possible intermediate states that one needs to consider. So when we sum over intermediate states, we can actually separate the sum into a set of levels with gamma 1 plus symmetry, another set of levels with gamma 1 2 plus, and gamma 2 5 plus, gamma 1 5 plus. So these are the different levels that actually are going to couple with the gamma 1 5 minus level by the perturbation Hamiltonian, which also has gamma 1 5 symmetry. Okay, so just let me do an example just to show in more detail how I can arrive in those expressions. So as an example, let's calculate the diagonal, one of the diagonal terms of that Hamiltonian. And specifically, let's start by calculating this matrix element between x and x, right? And again, following the expression that I have from second order perturbation theory, this is a sum of many intermediate states, and let's separate this sum. For instance, this is a sum. In the first part, I include only intermediate states with gamma 1 plus symmetry. So I have matrix elements like that, and the gamma 1 plus representation, it's a totally symmetric representation, and also complex conjugate. And the energy denominator, which is the energy difference between the gamma 1 5 minus and the intermediate level that I use the label n prime, and with symmetry gamma 1 plus, okay, at the gamma point. So this is energy, an example of one of the summations that I have to calculate. And the second term would involve intermediate states with gamma 1 2 plus symmetry, but remember, this is a two-dimensional representation, so I must also sum over the two partners alpha of these 2D representation. So this is going to be given by this guy, and it complex conjugate and then in the energy denominator, let me make it short. Let me write in the energy denominators delta n and n prime, okay? It's the energy difference between the level gamma 1 5 minus level that we want to investigate and the intermediate state n prime. Then we have another summation now for the gamma 2 5 plus, and this is a 3D representation, three-dimensional representation, so I have to sum of three terms actually, and here is for each, sorry, this is the perturbation Hamiltonian, and this is for each partner alpha and the complex conjugate. And the relevant energy denominator in this case. And finally, the last term, it's the intermediate states are gamma 1 5 plus, it's the same idea, right? And the energy denominator. Okay, so we have 4 different terms that we must consider separately. Let me call this 1, 2, 3, and 4. And now we go back to that table, and we search for the tabulated values for each one of these matrix elements. For instance, X H prime gamma 1 plus. If we go back to that table, this is precisely the complex conjugate of this guy, right? Because then this is going to be give me A1 complex conjugate H bar over M and KX, right? So this is for instance, this term is like that, H bar over M, Kx, and this is precisely the complex conjugate of that, A1 H bar over M, Kx. Okay? And you keep doing that. For instance, let's calculate the first term. So the first term is actually going to be given by a sum of the gamma 1 plus states, and then this product and the energy denominator and this is simply H bar square over M square Kx square. I can remove it from the summation, and the sum for all gamma 1 plus states that are labeled n prime, and this absolute value of A1 that could depend on n and n prime because has some orbital character in it, not only symmetry, and the energy denominator. Okay, this is what I call Fkx square. So if you compare this to this expression here, you see precisely that what we mean by F is a sum of this sort of term, a sum over all states at gamma with gamma 1 plus symmetry. Okay? Alright, so let's do one more. Let's calculate the case of a gamma 1 2. Gamma 1 2, the second term that involves intermediate states with gamma 1 2 plus symmetry, so is a sum of intermediate states this is the energy denominator, and now I have a sum over two partners of these 2D representations. So the first partner will involve this sort of summation, this this product. This is the first partner. And there is a corresponding term from the second partner. Okay. Now again, we have to go back to that table and see what the tabulated values for. Okay, so these are the ones. So that this guy A3 h bar over mkx is going to be there, and also this is when I couple with the first partner, and when I couple with the second partner, I get the complex conjugate. But since I have a multiplication of actually absolute value, it's just twice the same thing, right? So this is basically going to be equal to h bar square over m square. I have kx square, and then the sum over all states with gamma 1, gamma 1 2 plus symmetry, energy denominator, and actually I have here basically twice absolute value of A3 square. And this is precisely what I call G here. Actually, this is two times G, right? You can compare with this expression, and in the end, this is 2G kx square. Okay? So I'm not going to do all of them, because you know where this is leading us. So you can see that then. Well, let me just comment on the third term. The third term, if we go back here, it's a coupling between x and different partners of gamma 2 5 plus. But the x partner of gamma 2 5 plus is actually involves the wave function yz. So this is actually not going to couple with the x partner, the x polarization. But in the end, we're going to couple x to zx and xy. So in the end, we can notice that we are going to have to look at, you see, this is what I meant. This is 0, but there is a coupling between gamma 1 5x and gamma 2 5 y and z, right? So in the end, we're going to have kz and ky square. So I hope you get a sense of what's going on. So in the end, this term is going to be h1 ky square plus kz square. You can verify that, and the definition of h1 is this guy. And the fourth term, it's going to be h2 ky square plus kz square. Okay? So finally, then, if we sum over all different terms, the matrix element xx of the secular matrix is going to be f plus 2g kx plus h1 plus h2 kz sorry, this is kx square, and this is ky square plus kz square. I can relabel this constants. I can call this L, I can call this M, and this is precisely what you have here. Okay? So this is just the first term. You see the other terms are similar. You would calculate them in a similar manner, and after you do that, this is the final form of the secular equation that one has to diagonalize, and then one would find the energies of this manifold of threefold degenerate states gamma 1, 5 as we depart from the gamma point, right? Okay, so let's analyze this complete solution in some particular cases. For instance, let's look at the solutions at the gamma x direction, also called the delta line in a cubic symmetry. So in this particular case, I have ky equals to kz equals to 0, and let me call kx kappa, right? So I go back here and I do ky and kz equals 0. So you see right away that this matrix is going to be diagonal, and only kx is different than 0. And you can see right away that this is the matrix you get. So from that, I can immediately read the three possible solutions. Actually, I have one non-degenerate solution equal to L kappa square, and this is non-degenerate, and another twofold degenerate solution, M kappa square. This is twofold. So this is telling me that the prediction from group theory, if I have a band gamma 1, 5 minus at the gamma point, could be, for instance, the top of a valence band or the bottom of the, let's suppose it's some top of a valence band. When I go away from the gamma point along the delta line, this is gamma, so the three states which were initially degenerate here, they become they break up into one non-degenerate state and a set of doubly degenerate bands. Okay, and the analysis using K dot P perturbation theory, of course, it must be consistent with the compatibility relations that we have already discussed in the previous chapter. So compatibility tells us that a gamma 1, 5 minus levels, as we move away from gamma along the delta direction, splits into a delta 1 plus delta 5. And this precisely, this is a non-degenerate, this is a doubly degenerate state. So this should be a delta 1 level, this should be a delta 5 level. Okay? And this is consistent with K dot P. And you see already that that leads us to different effective masses. As we remember from the discussion of last time, the curvature of the bands are going to be related to the effective masses. So these two bands are going to have different effective masses, and the value of those effective masses would be given or known if we knew the values of those coefficients, right? Of those matrix elements. If we know how to calculate this, then one would be able to calculate the effective mass. But in practice, actually, this is the other way around. In practice, one can obtain the masses from experiment and use that information perhaps to evaluate these different matrix elements. That's one way to go. Okay, but group theory tells us at least what is the general dependence of the bands, the band dispersion, as we move away from this high symmetry points. So let's quickly analyze also another possibility, which is going away from gamma in another direction in the Brillouin zone. Let's go in the gamma, in the lambda line. The lambda line corresponds to the situation in which I have kx equal to ky equal to kz, and let me call that kappa. If we do that, that's the matrix that I get. Is a 3 by 3 matrix. It can be diagonalized, and the resulting solution is also a set of two energies, and one is non-degenerate, and this is when you do compatibility, this is what one called the lambda 1 band, and this one is twice degenerate, is lambda 3 band. Okay, again consistent with compatibility relations. So one could do that for any arbitrary direction in the Brillouin zone, and this is a very useful tool to at least to parameterize the band structure of semiconductors near either the top of the valence band or the bottom of the conduction band in many cases. So, and this has been used in early work, 1955, that actually this is pioneering work in determining the band structure of semiconductors experimentally, and these are used. This was done using the cyclotron resonance technique, and the cyclotron resonance allows us to obtain the effective mass along different directions in the Brillouin zone. And in this paper, Dresselhaus, Kipp, and this is actually Jean Dresselhaus, Kipp, and Charles Kittel determined both the band structure near the top of the valence band, which is what they call here hole, the mass of holes, and for electrons they refer to the bottom of the conduction band. And this is, for instance, the result for the top of the valence band. The top of the valence band, this would be threefold degenerate, but there is a split here we have not dealt with yet. This splitting results from spin orbit effects. We're going to discuss that in the future. But if we do not include spin orbit effects, the top of the valence band would be actually threefold degenerate, and it would be threefold degenerate, and with a gamma 2 plus symmetry. And what happens? So in this paper, they calculated the effective mass at the gamma point, and you can see here there are actually two different curvatures. This is leading to different masses. There's a band which is a little bit more flat, that gives rise to a larger effective mass, and another band with a larger curvature, which is consistent with a smaller effective mass. And this is how these two masses depend on the direction in the Brillouin zone. Okay, so this is along the 001 direction, and this is moving from the 001 to to the 111 direction, and this is to 110 direction. So there is some sort of anisotropy at the gamma point. The mass is different along different directions. But this is actually, in this work, if you look at the original publication, you're going to see all the expressions that we have discussed so far using K.P analysis and group theory. All right, let me consider another important case, which is the use of K.P, perturbation theory, at the delta point. So why is the delta point or the delta line important? It is important because the minimum of the conduction band in silicon, which is a very important material, so this is the silicon case. You see here some details of the band structure in different semiconductors. And for silicon, you see that the minimum of the conduction band is actually between gamma and X. It's actually 85% the distance between gamma to X, and there's a minimum here, and that's the minimum of the overall minimum of the conduction band in silicon. Okay, this picture is not for silicon. This is probably germanium. You see that for germanium, the minimum of the conduction band is in the L point, and this is just to schematically show different cases. For instance, the top of the valence band in group 4 or 3,5 compounds is threefold degenerate at the gamma point, and as I said, this degeneracy is broken if you include spin orbit effect. Typically, the minimum of the conduction band is non-degenerate at the gamma point for some also 3,5 compounds like indium antimonide, and so on and so forth. So this is schematic drawings of band structures of several important semiconductor materials. Okay. So one can see also these ellipsoids. Let me explain what those ellipsoids are. They represent what we called, in this case, electron pockets. These represent constant energy surfaces. So if you take a constant energy which is slightly above the minimum of the conduction band, this will be represented by a surface which is an ellipsoidal surface, and we're going to have actually for silicon 6 surfaces for the same energy corresponding to the 6 possibilities of delta lines. So delta, remember, is a cubic system, so there is in fact 6 different delta lines, plus and minus X, plus and minus Y, plus and minus Z, and for each of those directions there is these electron pockets. The band surface of constant energy at the conduction band for energy slightly larger than the bottom of the conduction band are going to be those ellipsoids. They are very anisotropic, and we are going to analyze that in a minute. This will lead us to different effective masses if we go along longitudinal or transverse directions from the minimum. Okay, so that's explaining why the delta direction or the delta point is important. So, and let's see now how we can use a group theory to analyze that. As a matter of fact, in silicon, the symmetry of this particular band, which is the lowest energy conduction band, the symmetry is delta 2. So in order to investigate what matrix elements are important in K dot P perturbation theory, one has to see, well, first of all, we have to, in the group of the wave vector at the delta point, the momentum P transforms like the delta 1 plus delta 5 representations. So this is actually related to Px, is a longitudinal component, and this is twofold degenerate related to Py and Pz. This is a transverse component. So if you look in first order perturbation theory, so let's look at the first order terms. One would have matrix elements like that. For instance, sorry, this is delta 2 prime, not delta 2. Sorry, the bottom of the conduction band is delta 2 prime. So delta 2 prime, Px, delta 2 prime, and since this is delta 1, you see that this is I have to see if this is non-zero. This is going to be non-zero whenever delta 1 times delta 2 prime is equal to delta 2 prime, and that's indeed what happens. So this is, in general, there could be a linear term, because this will give rise in first order perturbation to a linear term, which is non-zero. So in general, there is a linear term, linear in Kx in the band structure. But this is in general. But in this particular case, we want to deal precisely with the bottom of the conduction band. And just because it's the definition of the minimum of the conduction band, this linear term is going to be zero. Not because of group theory, but because it's the minimum. So this is zero if we consider the minimum conduction band minimum, CBM. Okay, so what about this is the longitudinal component of the momentum. What about the transverse component? So we have to analyze terms like that, and in this case this is actually zero, because delta 5 direct product with delta 2 prime is delta 5. So this is zero because of group theory. Okay, all right, so this is telling me that first order is not very useful, so one needs to go again to second order perturbation theory. And when we go to second order perturbation theory, what we have learned from the exercise that we just did is that one needs to look at intermediate states, right? And the intermediate states, depending on the particular matrix elements that we want to consider, we have to verify which intermediate states are going to give us non-zero matrix elements. So in general, we have to look at matrix elements of the following type. The state we're looking into, delta 2 prime, for the longitudinal case, symmetry delta 1, and some intermediate state. And we have already noticed from the previous example that in this case delta J must be equal to delta 2 prime. So the intermediate states that we need to couple for longitudinal components are going to be have delta 2 prime symmetry. Now, how about the transverse case? So for the transverse case, we have to look at matrix elements of this type. this transverse. And again, this is, since we have, we know that delta 5 times delta 2 prime is equal to delta 5. So in this case, we arrive in the conclusion that the intermediate states must have delta 5 symmetry. So only states with delta 2 prime and delta 5 symmetry are going to couple with these states, the minimum of the conduction band delta 2 prime. Okay? So, and you can see already that we are probably going to have, because of that, different masses along the longitudinal and the transverse direction. And this is precisely what happens. So to make a long story short, this is how to write the dispersion near the conduction band minimum in silicon, or in silicon actually. And you see that it's an ellipsoidal shape. There's a longitudinal mass. ML is the longitudinal mass, MT is a transverse mass. So this can be, dispersion can be well described using this equation to first approximation, okay, to first approximation. When you depart from the minimum of the conduction band, it gets more complicated. All right, and this is the experimental results from the same paper of the effective mass for electrons, meaning the conduction band, and you can see precisely these are the longitudinal and the transverse mass. The longitudinal mass was measured here in this paper, and this is still today a very well accepted and accurate value, roughly 0.98 of the electron mass, and the transverse mass, it's smaller, it's 0.19 of the electron mass. Okay, so this is transverse, this is longitudinal. All right, so now we come to the final application that I want to discuss in this chapter, which is the application of group theory to impurity states in semiconductors, and in particular to the Wally orbit splittings of those impurity states. So before we discuss that, let me do a brief review on the very fundamental properties of shallow impurities in semiconductors. What I mean by shallow impurities are either donor or acceptor impurities, and shallow meaning that the binding energy is very small. So they give rise to donor and acceptor levels which are very close to the bottom of the conduction band and the top of the valence band, respectively. And typically in a semiconductor, this happens when you substitute one certain atom. Let's take, for instance, a silicon crystal. All indicated here is a schematic view of silicon as if it were a 2D crystal, but you know that in fact it is 4D. But really, let's not pay attention to that aspect in this at this moment. What's important here is that each silicon atom makes 4 bonds with 4 nearest neighbors. Okay, in a 3D arrangement, this would be a tetrahedral coordination. But here is just I made a cartoon in a 2D sketch. So each silicon atom has 4 valence electrons, so it can make 4 different bonds with the neighboring silicon atoms. What happens then when I substitute silicon, which is a group 4 element, by, for instance, arsenic, which is a group 5 element. So arsenic has 5 valence band, 5 valence electrons. So it can use 4 of these valence electrons to make bonds with the neighboring silicon atoms, and there is going to be 1 extra electron that cannot be used to make bonds, and in principle this electron could be free to in this extended state in the conduction band, but arsenic also has 1 extra proton with respect to silicon. So there is a center of positive charge here that will attract this extra electron, and this will make a system which is reasonably similar to a hydrogen atom, right? A Coulomb potential, central potential, with an electron. So this could behave like a big hydrogen atom. That's why sometimes this type of impurities are also called hydrogenic impurities. So this electron is bound to this arsenic impurity. So it takes some energy to remove that and transfer this electron to the conduction band. And this energy is precisely the donor binding energy of this system. So the same idea can be done with acceptor impurities, using, for instance, a group 3 impurity like boron in silicon. And it's basically the same thing, but instead of an extra electron, you have an extra hole. And this extra hole will be attracted to the center of negative charge, but it's very similar. In both cases, then the simplest model to describe these systems are, as I said, based on an effective hydrogen atom. But we have to make 2 modifications of the hydrogen atom Hamiltonian in order to account for 2 features. First of all, we have to screen the Coulomb interaction in the simplest possible description, by the dielectric constant of silicon. And also, once this electron is free, is going to move through the crystal not with the free electron mass, but with the mass given by the effective mass of the conduction band. So we have to substitute here in the kinetic energy term the effective mass. Instead, we have to use the effective mass instead of the bare electron mass. Okay, but once you do that, you can basically disregard all the detail, all the atomic details of the wave function, and work with what we call an envelope function. This is an envelope function, which is a smoother and slowly varying function that are going to give me basically the solutions, the energies of the hydrogen atom modified by the dielectric constant and the effective mass. So this is a modified Bohr radius, and the effective mass goes in here. So what this is telling me is that the eigen energies of the system are going to behave very similar to those of a hydrogen atom. So it's going to be a hydrogen atom series, S, P, D states, so on and so forth. And the S, P, D character are going to be the symmetries of these envelope functions. Okay. So this is an example of what I'm talking about. This is some impurity in gallium arsenide. It's a donor impurity in gallium arsenide, and you see that there is some atomic scale oscillations But on top of these atomic scale oscillation, there is a broad and smooth envelope function, and this is precisely the envelope function that are the solution of this Schrödinger equation for effective hydrogen atom. AJ0 is the bottom of the conduction band. So this is an important comment, that the total wave function is not going to be simply the envelope function, but rather the product of envelope function times the Bloch's function, and the particular Bloch's functions around the minimum of the conduction band are those that are going to be important to write the total wave function of the electron bound to a donor impurity. Okay? So this is a review on the basic properties of shallow impurities in semiconductors. So let me consider some specific cases. The first and most simple, and the simplest example, it's a non-degenerate band and isotropic bands at the gamma point. For instance, donor levels in gallium arsenide. So, as I said, the effective mass Hamiltonian, the one I have just written before, has full rotational symmetry. It's like the hydrogen atom, so I should expect solutions with different angular momentum, S, P, D, etc. Right? But now we have to take into account now the fact that there is smaller symmetry in the system. In particular, and near the atom, the substitutional atom, the local symmetry is TD. So this becomes again the crystal field splitting problem, right? These are solutions of the full rotation group, and you have to see how these different solutions split under a TD symmetry. And we have done this exercise before. So the S levels, meaning the S envelope functions, will not split. The P levels will not split as well, are going to be threefold degenerate with gamma 1,5 symmetry. The D levels, originally fivefold degenerate, they will split into a gamma 1,2 and a gamma 1,5, twofold and threefold degenerate, and the F levels are going to split as well. Okay. So, because of the crystal field, these different hydrogen-like states are going to split in this manner. So, this is the first and simpler application of group theory. Group theory will tell us, depending on the particular crystal that we are interested into, will tell us exactly how this set of hydrogen levels are going to split. So, let's consider a more complicated case in which we have anisotropic bands, but still non-degenerate. Let's consider the idealized situation in which we have a non-degenerate band that is a single value, but anisotropic bands. Well, this is actually related to the silicon case we have considered before, but we focus our attention in only one of the valleys. We have 6 valleys, the 6 minima of the conduction band. But let's wait just for a minute. Let's forget about the other 5, and let's focus on only one valley. So in this case, you can see here again you have two masses, a longitudinal mass and a transverse mass. So this is a funny system that you cannot actually realize in atomic physics. Well, perhaps you can by applying some field, some magnetic field, but it's going to be more complicated. So, but it's a hydrogen atom. It's a hydrogen atom with two different electron masses, one longitudinal mass and one transverse mass. Okay? So this system actually does not have an exact solution. This problem has not does not have an exact solution. People work with variational solutions to this problem. But from the group theory point of view, what's important is that instead of the full rotation group, we must start from a lower symmetry group, which is the infinite age group. This is clear, right? Because there is one direction in space, in this case the z direction, the longitudinal direction, which is in different than the other two. So the symmetry is broken along one direction, and that reduces the symmetry from the full rotation group to the infinite age group. And then we have to do the same exercise, decompose the different states from the infinite age group into the cubic symmetry. In this case, this is the decomposition one has. Okay, and it's basically the same exercise we did before, but now using the as a starting point the infinite age group. Okay, so the third case we must consider now is the full analysis. Oh, this is wrong. So this should be p donors in silicon. It's the full analysis of a multi-valley semiconductor. So as an example, we have donors in silicon because we have to deal with the bottom of the conduction band, and now we have six different places in the Brillouin zone along the 6 different delta lines in which the energy is the same. Is the bottom of the conduction band has actually 6 valleys. Okay, so let's analyze initially what happens to an S-like envelope function in this case. So now we have to be more careful and write the full wave function as a product of an envelope part, this is the envelope part, and a blocks component. So this has a smooth dependence variation, and this is atomic-like variation of the wave function in atomic scale. And what this is telling me is that we have to start our analysis considering the 6 different valleys. So this is along so in K space, these electron pockets, 6 of them, right? And we have to start our description of the impurity state by considering a linear combination of all these 6 valleys. As we discussed before, in the simpler case, in which a donor state, for instance, in gallium arsenide, has just one valley, gamma point. So the wave function is going to be constructed from the blocks functions from that particular valley. If I have 6 valleys or more than one valley, then I have to consider possible interference between those different valleys. So our starting point are arbitrary linear combinations of blocks functions from these 6 valleys and multiplied by envelope functions. So, and those envelope functions, as I mentioned, this has no exact solution for this problem because it has this problem of an isotropic mass, but this is one of very popular. This is a very popular expression for the envelope part. You can see that this is, it treats in an isotropic way the z, meaning the longitudinal, and the xy, meaning the transverse effective mass. Is more like as we had different Bohr radii along those two directions. Okay, so it's not exactly that, but that's the general idea. Okay, so before I introduce the central potential, these different valleys have the same energy. So one in principle would have sixfold degenerate state, but this sixfold degeneracy is impossible in TD symmetry, right? TD symmetry will break this set of six states, and the way it breaks, you have discussed that many times already. It's the same idea in crystal field. So how can we find out precisely what are the different symmetries when we break the symmetry of these different valleys? We treat those valleys as in a similar way we have treated atomic sites, but we call them valley sites, and we calculate the characters of the equivalence representations for those valley sites. It's the same idea. We apply all the symmetry operations of the group, and we see how these different symmetry operations, which valley is preserved or invariant, and we count the number of valleys that are invariant for the different operations, and you see this is going to give me a reducible representation that will break up into gamma 1, gamma 1, 2, and gamma 1, 5 representations. Okay, so that's telling me precisely how the levels, the S levels, are going to split, because the symmetry of a particular level is actually the reducible representation. Is going to be the direct product between an envelope part and this valley site. But for the ground state, we are analyzing initially the ground state, right? The lowest energy levels, which has an S-like envelope function. So, and the S-like envelope function transforms like gamma 1. So this is going to be gamma 1 times gamma 1 plus gamma 1, 2 plus gamma 1, 5. And this is essentially gamma 1 plus gamma 1, 2 plus gamma 1, 5. So the level that I had initially, sixfold degenerate, will break into a non-degenerate level, usually the ground state, a twofold degenerate, and a threefold degenerate level. So this is how the ground state manifold of phosphorus donors in silicon look like. And you can go ahead and do the same exercise that we have done similar things before, and calculate the different coefficients. The coefficients for this expansion here are going to be given for the different representations by these factors. Okay. All right. Let's move on and let's look at the slightly more complicated case of p envelope states. Okay, so this is a little bit more complicated, because now we have to consider that the vector representation is going to be the sum of a longitudinal part and a transverse part. This is very similar to what we have done when we have analyzed a molecular electronic states, which had the longitudinal part, a direct valence, that means sigma bonds, and a transverse part that would give rise to pi bonds. Okay, it's the same idea here. So we split the vector representation into a longitudinal part and a transverse part. The vector in cubic symmetry transforms like gamma 1, 5 in TD symmetry. And well, the longitudinal part transforms like gamma 1, so the transverse part is subtract gamma 1 5 minus gamma 1. So we can then work out this direct product between the envelope part and the valley sides part, and it's going to be the sum of very many irreducible representations, and then we can calculate the longitudinal, which is associated to what it's called 2p0, and the transverse, the 2p plus or minus, like that. I mean, the longitudinal, it's going to be given by the gamma 1, right? Gamma 1 is longitudinal times the valley sides, which is the same splitting that we have seen for the S functions. And the 2p manifold. So again, this is, if we considered only the envelope part, this should be a non-degenerate level. But since we have 6 valleys, then we have 6 states, right? And here we have 12 states. So for the 2p plus or minus, we have to do this direct product, and this is going to give me four threefold degenerate states, 2 of the gamma 1 5 type and 2 of the gamma 2 5 symmetry. This is what we call the gamma 2p plus or minus states. So here in the energy diagram, you see precisely what we have seen before. This is the splitting of the 1s envelope function, and it has this splittings, and these are the 2p0, 2 plus or minus, 2p0 and 2p plus or minus. In principle, there is a splitting here, but it's very small and it's not so important. But in principle, each one of these levels is splitted in precise this different combinations. Okay, and the way to explore this energy diagram is by looking at optical transitions between those two levels. We're not going to go into detail, but there are selection rules that one can analyze, and you see that there are actually 4 different transitions, A, B, C, D, and these are helpful to analyze the energy differences between these different levels, and then pinpoint what are precisely the energy positions of those levels using optical absorption. And this is an important result in this direction. Okay. All right, so this is the end of chapter 13. These are the 2 problems that we want to do, and until next week. And once again, I thank you for your attention.